with players of the Detroit Seminole football team. These brawny guys are going to pit their strength against the power of the vacuum. And I'm going to help them. Thank you very much. You guys figured out what this is yet? We're recreating a famous experiment first carried out by German scientist Otto von Guericke. You see any way to hold that together? No. It's just silicone, right? So there's nothing in there that's going to hold it together. As with von Guericke's demonstration, we've got two empty hemispheres. Put that together. So now there's nothing in there but air, and now we're going to get rid of the air. Once we've pumped out the air, all that's left inside is a vacuum, or nothing. Our challenge is to pull the hemispheres apart. You ready? Go! Come on now! Come on! Come on, fellas! Come on! Come on, man! Come on now, pull it open, pull it! What's going on, man? There's nothing in there!
Air is strong!
All right, I'm gonna help you out this time.
Oh yeah, we gonna pull it apart now.
Pull! Oh my God! Von Guericke calculated that a force of almost 2,700 pounds would be needed to pull the hemispheres apart, which is why he used teams of heavy horses. No wonder we're having problems. Okay, put it down, put it down. What this experiment demonstrates is the awesome power of nothing. And unlocking this potential is about to become a crucial turning point in our story. A story that started with waterproof cement, which led to the building of huge aqueducts that supplied the water for use in double-action hand pumps. Pumps, which when combined with Greek fire, helped protect the city of Constantinople, whose scholars helped found the Renaissance, which in turn led to the building of spectacular fountains that inspired the experiment that revealed the existence of the vacuum. As so often happens in our story, the next great technological leap forward is born of a practical need, the need to save lives. Back in the 18th century, mining is one of the most dangerous occupations around. And as pits become ever deeper, those dangers increase. Not only do miners face the risk of sudden cave-ins and explosions, they're also vulnerable to another threat of coming across a hidden pocket of water that can flood a tunnel in minutes. Challenge: how to create a vacuum powerful enough to suck water out of mines. It was a problem that baffled many of the greatest scientists of the time. But in Britain, some clever engineers finally found the answer. And it involved heating water to create steam. It was, of course, the steam engine. When steam is cooled, it produces a vacuum. A vacuum that can be used to drive pistons and pump water. The power of this machine is just astonishing. It can pump the equivalent of an Olympic-sized swimming pool in just 4 hours. The steam engine is one of the most important innovations of the Industrial Revolution. It doesn't just change mining, it transforms manufacturing and transport. It changes the world. But it would take an enterprising Scot to push steam power to the next level. In 1763, a young instrument maker called James Watt is given the job of fixing a small-scale model of an early steam engine. Frustrated at not being able to make it run for more than a few strokes at a time, Watt proceeds to completely redesign it. a task that takes him more than 4 years, but which results in a radical new type of steam engine that is 4 times more efficient than its predecessor. But all this extra power was tricky to control.
This is the hand throttle, which controls the depth of the power stroke.
And that's just making sure it's doing the right level up and down.
Too big a stroke, and it will hit the stops. Too small a stroke, and it will stop. So that's getting a bit big. So if you come round here and stand...
Oh, yeah,
that's it, that's it. Close that about half a turn. It will stop. There it is. Now just lean on that.
All right.
Just push it down. That's it. And just open it a bit, and it will come back up.
And it's part of the job is to make sure that these delicate adjustments are always being maintained.
Yeah, you have to man this platform the whole time. You can't let your eye off them for more than two or three strokes.
Really?
Yeah.
Finding a way to regulate the power of steam would lead to a groundbreaking new technology that would revolutionize not only industry, but also warfare. Thanks to the engineer James Watt, the full power of the steam engine had finally been unleashed.
What Watt really needed was a way to manage this power. And to do it, he needed a pair of brass balls.
And believe it or not, this fairground ride explains how he did it. Because it's all about what happens to objects spinning around a central post. Physicists call it centrifugal force, and James Watt applied the concept to his new device. The centrifugal flyball governor.
The faster the central post spins, the higher the objects rise. When they hit a certain point, the throttle disengages and the engine slows down. As the objects descend, they hit another point and the throttle re-engages and the engine speeds back up. And that is how the centrifugal flyball governor maintains a constant speed. Simple, but revolutionary. Watt gives machines the ability to control themselves.
Adding Watt's governor to steam engines in mills and factories freed workers from having to supervise them around the clock. For every person working in a factory, dozens of governors and self-regulators toiled away in the background.
If steam engines are the brawn behind the Industrial Revolution, the governors are the brains.
And it's all thanks to a principle that we now call feedback control. The idea that a system can operate within certain set boundaries. Before long, feedback control was being applied to all sorts of mechanical technologies, like ships, planes, trains, and automobiles. And with the dawn of the electric age, control theory was used in telephone systems, amplifiers, and power grids.